Hello everyone, my name is Ciro Continisio. I'm a technical evangelist at Unity. I work out of the Brighton office in the UK, and my role is to go around, speak at conferences and showcase features of Unity, stuff that's coming up or stuff that's old but people don't know about. That's what evangelists do. So today I'm gonna talk about machine learning done through Unity. And specifically of a thing that we launched recently, which is called machine learning agents. But first, I want to explain a little bit what is machine learning for the ones of you who don't know. So machine learning is an application of artificial intelligence that provides systems with the ability to automatically learn based on observations. Here you see like a map of the different types of machine learnings. Of course, there's more, but So the process of learning begins with observations. In order to look for patterns and basically build like a behavior out of them. The one machine learning that we're going to look at today is the one in green. It's called reinforcement learning. So reinforcement learning, I guess the name is kind of self-explanatory and coupled with the image. Reinforcement learning is a method where the agents, so the ones who have to learn, they make observations on the environment, they take some actions, and then they discover errors or rewards. So we, the programmers, we reward or we scold the agents for doing something. And it's basically like, teaching the dog to sit down. So the dog doesn't speak our language, but whenever he sits down, he gets a reward, he gets a cookie, and then he will start associating the cookie with the fact that he sat down. So he starts learning, even if we're not speaking the same language. And we perform the learning in machine learning using something called neural networks. And neural networks is a computer system that's modeled on the human brain. So neural networks can contain from like a few dozen to hundreds to thousands of these artificial things called, artificial neurons called units. And these units are arranged in a set of layers. So you have an input layer, you have an output layer, and information, of course, travels through them. And in between, you have these things called hidden layer, where basically we sort of don't know what's going on. So we provide the input, then there's some stuff that happens inside. Of course, somebody programmed, but like we don't know as we're using the neural network. And then it spits out some data that becomes the behavior, the behavior that the neural network has learned. So going to Unity, as I said, the implementation that in Unity that allows you to use machine learning through Unity is called machine learning agents. It's been launched like a month ago or a month and a half ago through the blog. It's been announced. So specifically in Unity, right? That's how the machine learning agents work. You start with these things called agents, and they live in an environment. The environment is a Unity scene. And so agents perform actions on the environments. They do something. The environment reacts. There's something that happens in the environment, and you have this change of state. And then these states are fed back to the agents. So the agents can observe the states, and together with that, it gets some rewards that we program. So the agent performs actions, stuff changes, he sees new states, and he goes like, okay, I got this reward because I did this thing, and this is the new situation. And so the environment, as I said, it's a Unity scene. So if you look at the environment, which is like this dotted line, in Unity we do it through a series of game objects, as usual, and these game objects have components. So you start with a component that's called the academy, and the academy basically defines the general variables of the environment. The speed, the ability to like skip steps, and resolution as well, at which the environment runs. And then to this academy, you connect a series of brains. So brains are another game object that sits under the academy, and you can have as many as you want. You can have more than one. And as you can see, brains can be internal, heuristic, or external. I'm gonna explain what that means. So each brain is gonna learn through the training, and then you can have the agents that I mentioned before. So the agents can be like, as many as you want again. But each agent is connected to one of the brains. So, and they only have one, of course. So as you can see, for example, in this case, I have 2 agents that are connected to brain A, which is an internal brain, 2 agents that are connected to brain B, and then 1 for C and 1 for D. And so you create this environment, you place these game objects, and you write the rules. And then when you want to run the training, you connect it to an external environment, which is made in Python, and it uses a library called TensorFlow, which is made by Google. And it's the library that we use for machine learning. So the Unity environment, the one in the dotted line, communicates with the TensorFlow. TensorFlow basically handles the learning process, and then it spits out a model, which is a file, like a text file, that we import back into Unity. So as you can see, in this case, what is communicated with the TensorFlow is only the external brains. So those are the brains that we use for the learning. The other brains, we use them for playing back the learning. So once the learning has happened in TensorFlow, we extrapolate this model, we feed it back into Unity, and we use it with the type of brain that is marked here as internal. Just to give you a quick example of like some example projects that I worked on or that are included in the machine learning agents, an example of what you can do with machine learning. This is a very simple one. It's one that comes with the repository that you'll find online. And basically, the goal here is to teach these platforms, which are the agents, to balance the ball that sits on top of them. So the ball falls down, and then the platform has to learn to rotate to keep the ball from falling down. So in this case, you have the goal is to balance the ball on the platform, and the reward here that we give is at 0.1 for each step that the ball remains on the platform, and then we give a -1 when the ball falls for the platform. So we have basically two rewards here. This one is one that I made. It's a very simple one. It was my first experiment. So the idea here was that these cubes with propellers on top, they fall down with gravity, and they have to learn to stay afloat. So here the only input that the cubes have is to produce a push upwards. So they fall down, and they have to learn how much do they have to push to stay afloat. And so what I did to teach them is to give them a reward for each step, for each frame that the cube is still flying. And then as soon as they touch the ground, I give them -1. And then in time, they learn that when they touch the ground, there's something wrong. So they start applying this random force. And in time, they also learn how much force they have to apply. So as you can see, there are some, especially the one top left, he's like falling down, and then as soon as he almost hits the ground, it applies a lot of force and he pulls himself up. So I haven't programmed any of these. I just programmed the rewards, but the agents learn on themselves. This is a very simple example as well. It's like an arena where you have this capsule that is trying to push a cube outside of the arena. Here the only input is like moving left and right or up and down. And then the rewards, these are a bit forced. So they are like 0.2 if you're closing into the crate, and then 0.5 when the crate moves away from the center. So in time, the agent learns that he has to push the crate outside of the box. This is another one, very simple. So there's this ball falling from the sky, and then the agent has to learn how to bounce it, not to make it fall down. So again, similar stuff. It's like a +1 if the ball is still flying, and -1 as it gets further away. So the agent learns that he always has to be under the ball to continue like juggling with the ball. But these are very simple examples. So when I started playing around with machine learning with Unity, I thought, is it possible to use machine learning in a real game? Like, so let's make something more complex. And so we came up, me and a colleague, with this very, very simple game that we call the Roguelike. So we use this pixel art graphics. We wanted to keep stuff simple, because machine learning is quite hard. And we came up with this idea of these, basically, it's a very simple action game. You have the character moving in 2D, right? And then we thought one key element that I really wanted to push is that all the entities are agents. So both the player, both me, the human player, and the machine learning agents use the same script. The difference is that I provide the input my own way. I provide whatever input I want, and then the machine learning agents need to learn, and they are going to be controlled by the brain. And this way, I thought we could establish a common interaction language. So the action that I can do, the agents can do. And then we can, kind of speak together. And when I say actions, I mean moving left, right, up, down, and attack. That's the only thing that we introduced in this game. We wanted to keep things simple. So the goal of the game is, of course, surviving while attacking other entities. So you meet characters in this environment, and then you attack them, you lose life, and then you progress forward. So when we set up the training, the first thing that the first process that we had to go through was, what are the game actions? And as I said, I wanted to keep things very simple. So again, there's one action, which is the movement on the x-axis. One action is the movement on the y-axis, and the other action is the attack. And then you need to think about what you want the agent to learn. So what we wanted the agent to learn was to basically survive, as I said. So what does that mean exactly? That means that if they have a certain health, they want to keep that health high. So if the health is going down, they want to move away from the threat. So we wanted to teach the agent basically to attack the enemy, but if he was, at risk, then he would have to move away. And, in a simple AI, it would be easy just to calculate like the distance or the direction to the enemy and then apply a force in the other direction. But here we're not doing that. We're not explicitly saying move away from the enemy. We're just saying like, you're in danger, bad, like if you're there, bad, we're giving a bad reward. And then the agent should learn how to move away on his own. So the third step is, of course, to define what's right or wrong in this behavior and provide rewards or negative rewards to push the agent to do what you want to do. So the pseudo algorithm looks a bit like this. And as I said, I call it the agent step. I mentioned the step before, because this happens in physics. So who of you has used Unity before? Okay, quite a few people. So Unity has these two loops, right? It has the update, which is graphics, and then it has the fixed update, which is physics. The learning, the whole machine learning thing happens in the physics. Because as you know, the physics are like stable. They're like 0.02 seconds each step. And you want this learning process to be stable, right? Because it has a relationship with time. So it's performed in the fixed update. And you have this function, which is called the agent step, which is going to be executed every fixed update. And this is more or less how it looks like, right? So we said, OK, so how do we make this movement back and forth? We say, if your health is above 50%, so you're not at risk, then we say here that if the current distance is less than the previous distance, it means that the agent is getting closer to its enemy, then we reward it. Okay, so we reward the behavior of getting closer. If the health is below 50%, so this other branch of the if, then we reward getting away. We don't say get away, but we reward getting away, so that the agent learns in time. And in the beginning, the agent is going to perform like random actions. He's going to move like left and right, up and down. He's going to start attacking like randomly. But then when we reward these things, he's going to make the association and say, like, OK, maybe I have to get closer. And then when he gets a few hits and his health is below a certain amount, he makes the association, I need to get further away, because there's a healing function in the game. So if he gets further away, then he will, the health will go up again, and then he gets closer again. And so this is for the movement part. And then we have the attack part. And in the attack part, it's quite simple. Basically, the only thing I wanted to do here is I wanted to establish like a timeout, like a threshold, so that the agent doesn't attack like all the time, every single frame. So I set up like a second, and I say like, when you attack, if you attack again before this second, then I punish you. And the agent learned immediately that he doesn't have to attack like before 1 second. So we noticed that as soon as we introduce this punishment here on the right, they keep that in mind. And they learn that they only can attack, and then they have to wait 1 second before they give another attack input. I have to say, of course, that from that beginning thing, the initial algorithm has changed a lot in time. So the algorithm that we have today in the demo is quite different. Like all the initial ideas that we had, some of them were like completely wrong. So there's a lot of assumptions that you make in the beginning, and then you have to test them. And that will change the algorithm quite a lot. So before we go into the demo, I just want to give you some tips on rewards, the things that we learned. So one interesting thing is that the rewards don't need to be in this agent step, but they can be anywhere. So, for example, in our attack, there is a collider for the attack. We use it to check if the attack is like landed on the enemy. And that happens on collision enter on this collider. And in there, you can also assign a reward. So rewards are stored, and then in the agent step, they are collected. So you can build up these rewards for the frame, and then, when the training is happening, they are collected all together and they are evaluated. Then another thing we notice is that agents will find a way to exploit the rewards. So as soon as you give some rewards, the agents will find a way to get it. Like, for instance, one thing we notice is if you give a reward for getting closer, and we don't provide any other check, we notice that the agent does that. He gets closer, and then he gets away. And then he gets closer, and he gets away. And that's all he was doing. Because he learned that if he got closer, he will get some reward. So why even bother to go there and attack? He can, do his own life just moving back and forth, and like accumulating rewards. So they're like very, very primitive minds, right? They don't see the bigger picture. They see the reward, and they will go for it. So you have to be very careful where you assign rewards, and what rewards you assign, and the size of these rewards as well. So small details in the rewards can influence the learning process. For instance, here, the reward was assigned as a .2 divided by the square distance from the target. And this meant that because the distance is squared, the reward becomes very high when the agent is quite near, but very low when the agent is quite far. So the agent, when he was very far, he wouldn't even bother. He was like, why would I even move for like a 0.00001? I don't care. So he was just staying there, living his whole life. So, very little details can influence hugely the way the agents behave. So in this case, for example, this distance square doesn't work. You have to come up with some linear function that is connected to the distance. And then there's this big topic. So when you provide the actions and when you provide the states that the agent observes, you can use two spaces. You can use discrete or continuous. And they make a huge difference. So discrete means that basically the states and the actions can only have one value at a time. So it's like an enum or enum. So if you look at the actions, for example, in our game, initially we said, OK, you can move on the X, you can move on the Y, you can attack. And then we moved everything to the discrete. So now there's only one value that can have one variable that can have 6 values. You stay still, or you move up, you move down, you move left, you move right, or you attack. So the agents can only do one of these per frame. And that's a discrete state, right? And the thing with discrete is that it's easier to work with because the agents, they associate actions with reward more easily. If they attacked that frame and they get a reward, then that reward is probably because they attacked. When you use continuous and you have different inputs like left and right, up and down, and attacking all together, then the agents will do, OK, I'm moving here, and I'm attacking. I got a bad reward. What did I do wrong? He doesn't know. But with discrete, he's able to associate the input with the reward more clearly. And so he learns faster. Continuous, on the other hand, means that you can have multiple states or actions, and they all have float values. So as I said before, you can have movement X, movement Y, and you can have jump, a strength of the jump. So it's much more, it has more nuanced, but it's really hard to use because it can confuse the agent. and confuse you, because you're like, why isn't he learning? You know, I'm giving all the right rewards. It's because he's not associating the reward with the right input. Because every frame, a lot of stuff is happening, and then the agents can't figure out why. And then also they require more memory for training. So you see the thing, the hyperparameters, I'm going to show them. So you need to configure the training differently. And in Roguelike, in this game, we use continuous just for the states, because we want to provide health. So how much health? We want to provide can attack, which is a Boolean, really. We want to provide if it has a target, and then the distance from the target. So we have to pass a lot of data, and that's why we went for continuous, while for the actions, we went for discrete. So we mixed the two things. Just let me check the time. So the training scene that we configured looks like this. It's very simple. So basically what we did is we created a scene for training and then a scene for the game. And they're different. So in the training scene, we created like a smaller environment, simplified, and we placed the agents there so they can immediately start attacking each other, and they have an immediate feedback. Because if you place them in a huge world, they might never meet each other. So we wanted them to be there and to start attacking, to feel the pain, basically, and get immediately like bad rewards and good rewards for killing the other, and so forth. Let me give you a demo, so because I'm also kind of running out of time. So this is the training environment that we set up. As you can see, as I said before, can you read the text, more or less? Here you have the academy. So the academy has the parameters of the environment. So it has the max steps that the academy can take. It has the resolution at which the thing runs. It has the frame rate. And it has the time scale. So here I'm running the training at 100 time scale. So the training goes faster than actual gameplay, so they learn faster. And then under the academy, we have the brains. We actually have 3 brains here. One is for the player, which is a force. You see, I associate like just keys with actions so that I can play the game. Then we have a trained brain, which is the brain that is going to be trained by machine learning. And then we have a heuristic brain, which is basically a brain that uses a hard-coded AI, hard-coded by me. And so you see this little script here provides like random behavior to this brain. So you have 3 brains. One of them is going to learn, one of them is for me to play the game, and one of them is just a dummy that provides like good learning material for the agents that have to learn. So you see here we set up like 4 arenas. And in each arena we have these agents. There's this slime character. And this one is going to learn. And this one instead, he's the heuristic one. So he's going to be like a dummy. He's going to stay there, attack randomly, while the other one will learn, will like start trying to make connections between like the damage that it suffers with, you know, the action that it took and stuff like that. And once they kill each other, they get respawned just there in that arena. So we have this arena here, we have this arena here. So that's how we organize the training scene. So as you can see, the training scene is not gameplay, it's quite different, but it's a better environment to teach the agents faster. And also for us to experiment, because we had to go through several iterations, so we needed like a clean place to understand what actually was going on under the algorithm. So we have 4 arenas, and actually another thing we did is one of these slimes, they have like less health, so they get killed faster. So we get some that kill them, the opponent quite fast, and they start experiencing the fact that by attacking, they get rewards. Some others get killed quite fast, so they experience that by dying, they get a negative reward. And then all together, they're going to all feed into the one brain, which is this one, the trained brain, and all this data is going to be compared together, and it's going to make like the whole experience. So we build this like environment, which if you think about it, it looks a bit like these ones, where you have multiple agents that do the training all together and all contribute to the same brain. So they're all going to bring like their own experiences and go like, in my case I did this and I died, and in my case I did this and then I killed the other. Like, okay, so maybe we have to step back and just step forward to attack. So they all contribute to the learning process. So tips for the training environment. Different situations in parallel helps the agent to learn better. Then you can use these heuristic agents as the perfect training dummies. And then before launching an hour training, I would advise double-check your logic, which doesn't mean double-check your code. I mean, the code is going to compile, of course, but there might be something, well, there might be runtime errors first. So, play the game in Unity, and then you export and you try the training. And then the other thing is double-check really like the code. So if you look at the code, look twice, because if you run a training with a code that works, not like the projector, okay, it will spit out a model. You put the model back into Unity and the model will work, but you will see something wrong, and then you're going to make assumptions on it. You're going to go like, okay, so the thing I did wasn't working. Let's try this other thing. But maybe it was working. It was just, an error in the code. So what I mean is, like, you maybe were giving the rewards the right way, but maybe your if statement had, like a greater than instead of a lesser than. And then you're making a lot of assumptions on that. You're like, okay, this totally didn't work, so we have to give reward another way. And that, will bring you on the wrong path. So double check your logic before you launch a training. And then one thing you can do is you can launch one times speed training to see what's happening in the training before you launch a training that's like 100 times time scale. Because when it's 100 times time scale, you're not going to see it. So yeah, let me give you an example, because I'm really running out of time. So let me give you an example of how it works. So in here, what I want to do with the trained brain, I want to set it up to external. You see here, I have player, heuristic, external, and internal. I'll set it up to external, and then that's it. And then I can build. So I go to the build menu, and I choose which scene I want to build. I build into the Roguelike, Python. So I built here. I replaced my previous build. And then I have to launch the Python environment. So what I do is I open the terminal, I navigate to the folder where the build is, and then I run this line of code, which is called Jupyter Notebook. And it launches the Python environment, and then I open this thing called the notebook. And in here, I have basically the script that will run the training. So you have these blocks, you have to just execute them, and you see here we have these, we have these hyperparameters that I mentioned before, and these are the parameters of the training, and they will greatly influence the training. I'm going to give you some information on this now. You see they're all here. But let's leave them like this for now. So what I do here is I execute, I run all these blocks, run, and you see here it says load the environment, and here it says Academy started successfully. So cool, no errors. And we go here, run, and run again. And here the training has started. And Unity has started the game. You see here? The build is actually running. And it's using the resolution I gave and the time scale. So now it's running at 100 times faster. You see they're damaging each other. So, I made it so you can also scale the window. So now my computer is currently burning under the weight of 100 times simulation. And as this simulation is running 100 times faster than normal, you see here it's spitting some values out. So if I click here it says mean reward. So it's giving me the mean reward for those 10,000 steps. And then it's going to keep running the simulation, and this mean reward is going to change now. And it's currently very bad. So the agents are not learning anything. So they're doing all the wrong things. They're probably dying against like the heuristic dummy that I placed. But in time, you should see the mean reward going up. So as this spits out more lines, you should see the mean reward like slowly going up as the agents makes association and go like, okay, so that time when I got the good reward, I did that, so let me try again. And they start, tunneling down into the behavior that maybe you wanna get. So this is like growing very slowly. I'm gonna let it run a little bit more as I keep on with the presentation. So yeah, you observe the mean reward. and you stop when it looks stable, then you export the model and you import it back into Unity. And then you set the brain to internal, sorry, and you play the game. So how are we going to do this? We need to stop this training. I think we need to get to, let me do another one. Okay, it says save model. So I stop this block, and then I go down, and here I have one line of code that will export the thing. So I run it, and it says, I exported the model. Cool. So let me get the model. So I go in here into, I think it was models, PPO, and you see this file here. This is the file that I can use back into Unity, so .bytes. So I go into Unity, I close this window, and I go into here. These, as you can see, they're like a bunch of models that we trained before. There are some that are not really working. And then I right-click, reveal in Finder. Okay, the two windows are in different spaces, of course. Can I do this? No, I have to do this. So I bring the model back into Unity by, replacing the one I had before, and then I go into Unity and I say to this brain here, which you remember was set to external to be able to be trained, I set it to internal, and I say you are going to use this model here. And then I can press play, and I'm actually seeing if it doesn't. No. Okay, this is a stupid thing that Unity does sometimes. Yeah. It's some kind of permission-based thing that. Whatever. So I think it's, no, this is the training grid. Yeah, so I feed back the model that I just trained, and I press play. And now we're basically seeing the agents down there. So these ones here, I think, the most stable one. No, this one. They are the ones that I just trained. So this one here. So as you can see, it's just moving around randomly, it's attacking randomly, because I didn't train it too much. So it's still in the random phase. But as you see, it works. And then these ones are the heuristic ones. We just stand still and attack every now and then. And I think this one here is the player one. So if I can actually play around and attack this agent and fight and test if it works fine or not. Of course it doesn't, because I didn't train it too much. But that's what I say when I say that I wanted to have like a common language. Because if the agent that I control has the same language as the other agents, then I'm able to, check if they interact with each other in a good way. I think I'm going over time. So yeah, I'm gonna skip this part, I guess. I mean, these slides, I can provide them to you anyway. The only thing I wanted to show you, because I worked so much on it, is the actual environment. So if I go into scenes and I go into main, so this is the actual game. Oops. So yeah, so if I press play, that's what the game should look like, more or less. So you have the character controlled by me, which is an agent, but it has a player brain. So I'm providing the input. So I'm the god of that brain. And then you have these agents here, which will try to engage you, and I can attack them. Of course, I made them very, very simple to defeat. But as you can see, now you can use these agents in a much bigger environment. And what I did is I look for the player when it's nearby, and then I leave it to the machine learning. So, I mean, this is not a very trained model, but the idea is that if you train the model well enough, then you can use them in a bigger environment to make a proper game, which interacts in a much more interesting way than just a hard-coded AI. So, yeah. Again, I went a little over time, so this is it. Thank you for the attention, and if you want to get the demo, I have this small survey. I'm just going to ask you for the email, and then I'll send you the demo, because I'll send you the demo and the slides. And the demo is a repository, so you can pull the code, and you can look at this demo and possibly customize it for yourself and play around with it. And I'm also going to send you more information on where to find the machine learning agents, documentation and stuff. All right, thank you.